Assalamualaikum warahmatullahi wabarakatuh. Okay, in this video, I would like to continue on AES topic. Okay, for this slide, okay, in this slide actually, it supports or it gives the reason, the limitation, okay, the limitation of AES. That not suitable for simultaneously analysis of multiple element. That means analysis of one element per unit time. Okay, if you can see from the slide, actually all the points indicate that each element require different flame condition in order to give the maximum intensity or maximum signal. Okay, if you still remember, in AES, flame function as atomizer and also excitation source. Okay, I can give example. Okay, if we have a three element, with one element are considered very thermostable element. That means its oxides are difficult to decompose in order to release the atom from its oxide. Okay, in this case, the flame, okay, in order it to be efficient or effective atomizer, for this type of element, it require a very high temperature. But for another element, okay, it does not require that high temperature. Okay, for to release the element from its sample metric. Okay, the problem is when we use a high temperature, in general, it leads to ionization interference. So there's lots of issue when we want to analyze element, multi-element using AES because of the limitation from the flame. Okay, once when all the element needs different condition of flame for the excitation, that means they will give different behavior, or they will give different trend. Okay, in terms of the signal. Okay, if the what we call that, if the the temperature of the flame are not high enough, we expect not much atom are released or free from its sample metric, and then the population of the atom in the ground state, okay, is less compared when the right temperature is high enough to release all the atom from its sample matrix. Okay, so if the population of atom in the ground state are lesser than it should be, that means the populations of atom in the excited state also become lesser. Okay, so these are the limitation. Okay, limitation of the flame AES, especially. Okay, you can use all these three all this information to support the reason why flame AES is not suitable for multi-element analysis. Okay, because of that, okay, we need to find another excitation source for in AES technique. Okay, so plasma is one of the example. Okay, but before we further go details, okay, the use of plasma in AES, okay, we need to understand what is plasma. Okay, first, plasma is the 4 states of matter, okay, in addition to the solid, liquid and gas. Okay, plasma, okay, actually has been discovered a very long ago, in 1897 by Sir William Crookes, which is a Britain chemist. Okay, the plasma, okay, if you realize or not, okay, the whole universe, okay, the matter in the whole universe, basically the stars, okay, are made up from not made up, is in the forms of plasma. Okay, and these are rarely seen in Earth. Okay, lightning and sun, okay, they also okay, show plasma. Okay, basically the composition in the sun and also in the lightning, okay, they are in the form of plasma. Okay, plasma, sorry, okay, now we, okay, plasma, okay, long time ago people also known plasma as Saint Elmo's fire. This okay, plasma can have a lot of name. One of it is Saint Elmo's fire. Okay, okay, how we can interpret, okay, so basically what is Saint Elmo's fire? Okay, Saint Elmo's fire is a plasma, okay, blue, bright blue or violet glow of plasma that produce, okay, during that produce from the sharp pointed object in here that known as a mass. Okay, MAST. Okay, this is the we known as a ship mass. Okay, this ship mass, okay, during the thunderstorm, okay, it will causing existence of electric field. Okay, this electric field is created during thunderstorm because there is a different, okay, different in very high voltage between the atmosphere and the ground. Okay, and because there's a present electric field around the mass, okay, this will cause ionizations of gas molecules in the atmosphere. For example, air molecules, nitrogen, and etc. And okay, and all these chemical species in the air, when it undergo ionization, okay, in such a way when the equal number of ion and electron are equal, the plasma are formed, and this plasma we can see in the form of like a glowing blue or violet, okay, glow, okay, like a glowing blue or violet. Okay, sometimes people can say like a spark as well. Okay, so okay, this phenomenon is known as a Saint Elmo's fire. Okay, in those days, okay, when people are traveling, okay, using a ship during the thunderstorm, especially at the end of the storm, okay, before it stops, okay, they will observe this kind of plasma that at those days they call as a Saint Elmo's fire. Okay, how they call it? Okay, not how. Basically, this they, okay, how they give, okay, how they give the name. Okay, it's named after Saint Erasmus. Okay, this guy. Okay, he's a religious. Okay, he's a religious guy. Okay, Saint Erasmus, the patron saint of sailor. Okay, so what happened is why they name St. Elmo's fire, because they believe that, okay, when they're having a thunderstorm, okay, when they see the presence of this spark, okay, that means the storm will stop. So it's a sign of good omen, and they see this good omen because they believe this Saint Erasmus has prayed and blessed for their journey to be safe. Okay, that's why they call it as a St. Elmo's fire. But St. Elmo's fire actually is a plasma. Okay, another name is a plasma. Okay, plasma in the color of low, bright blue or violet. Okay, interesting, right? Okay, now we go to definition of plasma. Okay, plasma is a ionized gas, okay, with an equal amount of cation and electrons, and has the capability to conduct electric. Because there is an equal amount of cation and electron, that means the net charge of the plasma is 0. Okay, here I listed, okay, several ways to generate or produce plasma, okay, but in your syllabus, okay, we only need to know how we can generate plasma using inductively coupled plasma. Okay, so in the ICP, okay, the main component is the ICP torch, where inside the ICP torch there are 3 concentric tubes that usually made up from quartz. And why they said there's 3 concentric quartz tubes, because these tubes acting as a divider, so that so that 3 types of argon gas can flow into the torch, inside the torch. Okay, so the tubes, actually we call it as a outer tube, middle tube, and sample injector tube. Okay, for the outer tube, you can see that, okay, the plasma gas, actually plasma gas, auxiliary gas, and nebulizer gas, actually it represent argon gas. Okay, they give different names because to represent different function of the gas. Okay, for example, like plasma gas, if you can see here, it will flow, okay, between outer tube and middle tube. Okay, it called plasma gas because it carry argon gas when it go towards here. Okay, in this, actually this is the right direction here, is similar like direction here. Okay, the direction of the direction okay, the direction of the argon gas, okay, is flow from downward to upward. Okay, downward to upward. Okay, okay, this is the similar, okay, presentation. Okay, so you imagine the plasma gas will flow between outer and middle middle tube, and we call plasma gas because, okay, it carries argon gas to this direction, and this argon gas will converted into plasma. Okay, for the auxiliary gas, okay, the auxiliary gas will enter, okay, between middle tube and sample injector. Okay, the functions of the auxiliary gas is to change the position of the base of the plasma relative to the tube and the injector. Okay, for the nebulizer gas, it will flow from here, Okay, that means nebulizer gas, okay, it flow, okay, in the flow from inside here, okay, it flow inside here. And okay, nebulizer gas, as you can see, it carry, okay, argon gas that carry sample, okay, where the sample in the form of aerosol, okay, aerosol towards here, okay. So okay, now we go how we can generate a plasma. Okay, so the keyword here, okay, we can generate plasma when there's an interaction between the argon ion, actually not argon gas, argon ion with the magnetic field in the presence of radio frequency. Okay, we go one by one. Okay, so okay, first when we turn on the torch, okay, first I would like to introduce the main component in the ICP torch. First, of course, the torch. Second, the radio frequency coil. Okay, these are the radio frequency coil. Okay, wait. Okay, so okay, this one, okay, this one, we call it as a radio frequency coil, and this coil normally made up from copper, and we have a radio frequency generator that connected to the coil. Okay, the functions of the radio frequency generator is to supply radio frequency current. Okay, so that's the main component. So first, when we turn on the torch, okay, there will be radio frequency flow within the coil or the copper coil, and okay, this will generate magnetic field, alternating magnetic field. So this one is magnetic field. Okay, so okay, radio frequency actually is a under category electric field. So presence of electric and magnetic will create electromagnetic field. Okay, so okay, now there's a magnetic field. Okay, so what happened? Okay, this argon gas, okay, we flow. Okay, we imagine the argon gas come from argon gas, plasma gas. Okay, we imagine the one that I show here, that I draw here, is a plasma gas. Okay, plasma gas. Okay, there's an argon gas that flow. We call plasma gas because the argon gas does not consist of sample. Okay, sample matrix. So the argon gas move from this direction to upwards. Okay, when the argon gas move into the direction, okay, before, okay, somewhere along here, okay, there is some high voltage of spark that will be applied towards the argon gas in here, and this spark actually will pull the electron from the argon, that causing the argon undergo ionization process. So in here you will get argon ion and also electron. Okay, so what happened here? Okay, there will be interaction between the alternating magnetic field and argon ion and the electron, okay, where this interaction will cause all the ions and the electrons to move in a circular path. You can see here there's like a circle, okay, to move in the circular path. Okay, actually when they are moving, this circular path also known as a annular path. Okay, because the ion and electron are forcing, okay, to move in the circular path, they give some resistance. This resistance, okay, we known as ohmic heating. We call it as a ohmic heating. Okay, and this ohmic heating, okay, give the plasma temperature maximum up to 10,000 Kelvin. Okay, how the one thing, okay, you have to notice that, okay, the argon gas is continuously supplied into the system, okay, because it's moved, it possesses kinetic energy. At the same time, okay, this argon gas will collide with argon ion and electron that has formed previously, and the kinetic energy that are obtained from the collision and also from the movement of the gas, okay, can sustain the plasma temperature at the temperature of 10,000 Kelvin. Okay, I think that's all for now. Thank you.